And thanks very much, Rosemary, for this invitation. It's a great pleasure. I mean, what I want to discuss today is something that hopefully serves to illustrate a bit the utility of this kind of approach and attitude that you have towards scientific research, if I can justify that a little, because that's not so terribly different from my own way of thinking. So I want to tell a story that goes back really to when I did my diploma thesis at TUM. That was in 2005. And of course, there are things that you're supposed to do during your diploma thesis. You're supposed to work with other people's code to simulate stellar explosions. And then some people try to understand, to get to the basics and understand what's going on, and write their own hydrodynamics code. So I tried to, using something that I learned, just discretize the equations of hydrodynamics in spherical polar coordinates and spherical symmetry with a very simple description of the microphysics, so a double polytrope plus some thermal contribution there, to just be able to reproduce myself some very basic problems of adiabatic collapse of iron cores and then the bounce. Yeah, so stuff that was known for since the 80s, yeah, analytically. Yeah, but why not code that up yourself, yeah? And of course, if you're a poor student who's supposed to do other things at the same time anyway, you don't necessarily develop the highest grade code, so you just go with simple recipes, exactly sort of the kind of thing that we're teaching now in ASP 3162, which got off the ground very much thanks to you, Rosemary, right? So, and Daniel. And Alex, yeah. So, of course, well, then what happens? So you can look at the physical results there and be sort of happy with it, right? So your hydro code is able to follow the collapse of a polytropic iron core, and then it bounces as the equation of state stiffens, density goes up, overshoots, and the whole thing rings down a bit, and then the star expands a bit again. So that tells you, okay, basic boxes ticked, so this can reproduce sort of the essential qualitative features of such collapse dynamics. But of course, what you also want to have a look at is some metrics for how well your code is actually doing quantitatively. And one of the important metrics to look at there is, of course, for a collapse problem, like collapse and explosion problem, is total energy conservation. Yeah. Now, total energy conservation is quite fine if you're doing gravity, if you're doing hydrodynamics without gravity or with external gravity. But for self-gravity, it's actually not quite trivial. Yeah, because, of course, any physical, astrophysical system obeys total energy conservation if you include self-gravity. But unlike the conservation of total energy without gravity, that doesn't come about directly as a result of some local conservation law, d over dt equal plus divergence of some flux equals 0. So the conservation of total energy for self-gravitating system is a somewhat complexish result of the application really of Green's first identity to the self-energy gravity term, which has this factor 1/2 in here incidentally when you multiply the density by the gravitational potential and integrate over it. Yeah, and if you know your vector calculus, you can figure out that the rate of change of the rest of the energy is exactly opposite to the rate of change of this integral over rho phi half over volume. Yeah?
You lose a mark for leaving out the dot.
Oh, sorry, Rosemary. Good. Yeah. So, as I said, there's no simple way for that to be changed into a local conservation law, which is what we'd always like, because that's a nice path towards solving equations of fluid dynamics conservatively. And consequently, so if I did this with my simple code, energy conservation didn't actually look so great. Yeah. That's total energy, and this is the time where this whole thing has fully collapsed and bounces. And you see it's not Not really impressive, because this doesn't even conserve the sign, right? So that's bad. So what did I do? I said, well, that's a bit disappointing. And despite the fact that I was supposed to do other things, I was not quite happy with this and tried to tinker around with that. There is, of course, a potential solution for this, which, however, so some of you may not know, for fully implementing hydrodynamics in a formally flux conservative manner. But it unfortunately doesn't help you really with numerical solutions. Does anyone know how to formulate the equations of fluid dynamics fully conservatively with self-gravity? Yeah, well, I mean, you're still cheating because you're counting on, with gravity, you're still counting on the way your integrators do the gravity terms symplectic, with some symplectic integration. Yeah, so you're not doing it exactly, I guess. We can discuss about that. Yeah. Anyway, there's formally a way you could actually implement the equations of fluid dynamics in a fully conservative manner with self-gravity. Those of you who know a bit about general relativity will not be surprised by that, because that's essentially the limit of the conservation of the components of the Landau-Lifshitz pseudotensor in the Newtonian case. You can derive sort of an effective conserved energy density of the fluid plus the gravitational field, and similarly fluxes of that energy density. But this expression is a bit ugly for numerical implementation for several reasons. One of the things that really offends any decent numericist is that you actually have time derivatives in your flux quantity. That's fishy, right? So that doesn't really lead anywhere. Yeah? But there's one possible remedy there that I sort of played around with. Yeah? So you can try and shift the various terms in your derivatives of the fluid energy equation around. Yeah? So you can try to sort of push your potential inside the conserved energy density and inside the flux. That, of course, comes at the expense that you get a source term which has a time derivative of the potential. Yeah? That's fine mathematically. You can implement that by sort of first solving the equations for this thing equals 0, and then you add this term. That's called an operator split. That's fine. The educated numericist is probably still very unhappy about this, because there's a rule: you should never keep such a large quantity here added to your energy density. It doesn't go well if your equation of state is very degenerate, internal energy is very low. And if you add and subtract the potential every time step to get back from this to the internal energy, very fishy. Yeah? But of course you're desperate as a young student, so you try nonetheless, right? So first order time integration, then second, and then when I took care of, still wasn't quite so happy about this, then I said, well, what about implementing this term here with second order accuracy? Now, if you zoom in, you might ask, is this perhaps a bit too good to be true? Yeah. Did I make a mistake in the implementation? Well, I'll come back to that later, actually. For now, the thing is, since you have this still has this nasty disadvantage that this scheme actually subtracts and adds the energy of the potential at every time step. That was not really something that I followed up. I said, well, I'm using other people's code and they have much higher accuracy of integration anyway, so the problem isn't that big, so don't worry about it for now. Okay, so what did we do other than that? So, well, then I started my PhD, and during the PhD, of course, you got to get a few other problems solved, including ones that people actually care about. So one of the things that we eventually attacked during my PhD thesis was long-term predictions for neutrinos emitted in a galactic core collapse supernova. That's very important for the neutrino detectors to interpret the signal that they will see at the next galactic supernova. The historic detection of neutrinos from 1987A, you see the events here as they were detected in time in 1987A, in 1987, in what was then, what is now Super Kamiokande, Super K. That had thrown up a little bit of a puzzle because the time over which the neutrinos are emitted is actually a bit on the short side, so sort of 5-6 seconds or so. That's where the bunch of them come out. And models of the opacities of dense neutron star matter really struggled a bit with that. That's sort of things coming out too fast. Yeah. So at that time, we were happily in the position that our neutrino transport code was finally able to run simulations to such long times, to such late times. So we were very eager to explore now with updated opacities what the neutrino signal would look like. And it looked like this, luminosities and mean energies. And if you know what cooling means, just need very basic physics for that, you might not be all too happy about those results either, right? Because this is not really a neutron star that's cooling. The temperature's not going down, luminosities are not going down. So initially we had to think a bit about, well, was that physical? Well, we got suspicious, right? And then we wondered what might be the cause of that. And now can you put the 2 and 2 together? So the cause is actually lack of energy conservation. Yeah. So now this actually struck with one of those good production codes, non-conservation of energy for self-gravitating systems. Yeah. So now it turned out to be actually useful that I had played around with equations a few years ago, right? But we still had this little problem that the implementation was nasty, right? Shifting the gravitational potential term inside the conserved quantity. Yeah. So how to get rid of that? Well, a bit more of vector calculus and finite differences does the trick. So basically, in this first operator split step that we had, we're treating the phi as constant in time anyway during the operator split step. So there you're actually allowed to move this thing out and rearrange your equation slightly. Yeah. And develop a nice operator split scheme that sort of expresses this rate of change of internal energy due to stuff moving around in the gravitational potential very neatly. Yeah, you don't need to add or subtract total energy. You basically just budget energy changes where stuff is effectively jumping around in the gravitational potential. And then you have 2 other steps that can be merged that account for the change of the gravitational potential in time. Fortunately, this is actually something that can be done extremely efficiently in the code that we were using. So thinking about everything properly instead of rewriting your whole code, it's just changes of those few lines. Yeah. So that allowed us to get those long-term neutron star cooling simulations done. Showed one very interesting effect among others, which is that correlations of the nucleons at high density actually reduce the opacity of neutron star matter such as to give you the short cooling timescales seen also in supernova 1987A. Did have a bit of an impact.
It must have been so exciting.
Yes, yeah. Got a good diploma thesis done by this student that I was supervising at the time. And that is basically the end, so I don't want to overdraw this, so I don't have too much time. But there is a little homework problem in there hidden for you, Rosemary, which is why with this very crappy second order code was I able to achieve exact conservation of energy to machine precision? Yeah? And it comes down, so the part of the solution, it comes down to this. So in the analytic case, what helps you to enforce energy conservation is Green's identity that allows you to change rho times, oh, there's a Laplacian missing here, of phi into two gradients. So if your gravitational potential is defined appropriately, with that kind of scheme, you effectively get the exact discrete analog of Green's identity there.
Yeah. Go back a sec, though. You said there was a grad missing, but how can there be?
Here.
It's got to be a scalar. Del squared. Yeah.
So del squared, yeah. Dot product. Yeah.
Right.
Ah, yes. Oh, okay, there's actually no Laplacian because this would be a Laplacian of phi. Yeah. Right. So that's the key. So in the end, it turns out that you can change the resulting numerical change of internal energy per time step to something which is essentially symmetric in the gradients of the potential at both time steps. So that will be your homework problem. You'll get the solution. Yeah. Right? So no conclusions really, right? So I hope this shows the merit of this kind of approach that I think, well, Rosemary likes, and I like, and others in this room very much like to science. And I'd like to conclude with some remarks by people much more knowledgeable than myself to underscore the importance of this kind of approach and also the relation to the artistic component of science by the famous German sociologist Max Weber. You notice there's a slightly tiny emendation to make this fit exactly to the important person in the room. Yeah. I think Weber forgives me because his wife was actually one of the pioneers of women in academia and the first speaker representative in the Constitutional Assembly of the state of Baden after World War I. So one of the first democratically elected women in Germany to play a major role. Yes. Rosemary. So because of that, artists never really retire, right? So no goodbyes.
No.
And
Thank you.
that's my bow to you.
Thank you.